guys, in this video we are going to learn about the ternary ionic compounds. As a reminder, a binary ionic compound is going to be one that is composed of two types of atoms. Here on screen we have magnesium and chlorine, so that is two different types of atoms. That counts as binary. For ternary, we are talking about the composition of three or more types of atoms. So here in our example we have magnesium, chlorine, and oxygen. And again, we do not necessarily look at the subscripts that will come into play in a few more lessons. So let's go more into depth. In previous lessons, we have already learned about oxidation numbers, but it is a good practice to go back and review that information. So remember that oxidation numbers are the number of electrons that are either lost or gained to achieve the full valence shell configuration that we call the octet rule. So in a previous unit, we learned about the different trends and we looked at the numbers. And if you didn't get a chance to label them on the periodic table, please make sure that you do so this time around. Here we have the numbers at the very top and at the bottom of the periodic table. So please pause the video and make sure that you label the main groups on your periodic table. Additionally, we are going to now label some other of the more common elements in the transition metal group that we will be using. So here on screen we have a bunch of different ones, and if you notice, they don't actually follow a specific pattern. So the reason we want to label them is so that we don't have to memorize them. These are all different oxidation numbers. Again, you're not expected to memorize them. You are expected to have them labeled and have access to them as you continue on with the course. So please at this time, take a moment, go ahead and pause the video and make sure you are labeling the oxidation numbers for all these transition metals. Let's talk about polyatomic compounds, because all we've done so far is talk about ternary ionic compounds that are specifically, like we said, ionic compounds that have three or more different types of atoms in them. Well, every time we see a ternary ionic compound, we're going to observe a polyatomic. Now, we have talked about polyatomics in the past, but we really haven't gone into depth. So let's just look at the word polyatomic. Poly means multiple, atomic, well, it means atom. So what we're talking about is a compound that is composed of multiple atoms. And that's exactly what a polyatomic compound is. For the most part, they are covalent compounds that have an overall charge, designated name, and charge. So what I mean by that is these are groups of atoms that are given a name and have a specific charge that we associate that have the ability to form ionic compounds. Now, whenever we look at polyatomic compounds in ionic, we still want to make sure that they equal to 0. So again, you're not expected to memorize a lot of this information. You are expected to have it available as a resource. So on your periodic table, the place where you will be able to find them will be on the STAR reference sheet. I believe it's the 3rd or the 4th page of it. And here on screen, I have them circled. So that entire list are the polyatomic compounds that we are going to be looking at in this class. So whenever we talk about ternary ionic compounds, we're talking about an ionic compound that contains a polyatomic ion. So the nice thing about them is that they follow very, like I said, they have their own name. So you don't have to go back into the whole, as we see here on screen, you name the metal, then a Roman numeral, and then you have the non-metal, and you change the ending to IDE. When we talk about ternary ionic compounds, like I said, we have a polyatomic in it, and polyatomics come with the name. So that's really nice because there's nothing really you have to do other than find its name. So the reason I have this slide here is because just because the polyatomics come with their own name doesn't mean that we have to forget about the Roman numerals, because remember, those are specific to the transition metals that have multiple oxidation numbers. So let's look at a few examples so that you guys can see what is it that I mean. So we're going to look at it from two different perspectives. We're going to go from the formula to the name. So right here, the first example on screen, we have Na2CO3. First thing I want you guys from this point on to always do is to first identify if we have a binary or a ternary. Because again, if it's ternary, then it means that it has a polyatomic in it, and then we can find it on the list of polyatomic ions. So right here on screen, we have 1, 2, 3. So that's ternary. That tells me that the second part of the formula is going to be a polyatomic. So we go back to the idea of naming the metal, then if it needs to, having a Roman numeral, and then going with the name of this scenario, the polyatomic, because this is ternary. So we're going to write sodium. And I'm not going to write down a Roman numeral because I know that sodium only has one oxidation number, +1, right? And CO3, I'm not going to go on my periodic table and find the name of C and then O, right? I'm not going to do that because this is a ternary. And ternaries, like I said, have a name, polyatomics, right? So let's look for CO3 on the list of polyatomics. And again, you're not expected to memorize this list. You are expected to have it available as a resource. So if we look on the list here on the left, we can see that carbonate is located right here, right? CO3, and its name is carbonate. I'm not going to change its ending because remember, polyatomics have a name and they have a charge. We don't mess with those things. They are standards. So the name of this particular formula will be sodium carbonate. And again, I am not bothering with Roman numerals because sodium is not a transition metal that has multiple oxidation numbers. So it does not need a Roman numeral. So that's it, sodium carbonate. Let's look at the second example. We have CO, Cn. This right here is another example of a ternary ionic compound. We have cobalt, we have carbon, and we have nitrogen. So I know that I'm going to name my metal cobalt, and I know based on the location of cobalt, I know that we'll have multiple oxidation numbers. So I'm going to have to go back and look at that to figure out what are the charges that they have. And then Cn, it's in parentheses. The reason it's in parentheses is because there's 3 of them, okay? So don't be confused by the parentheses. Again, they just indicate how many of them you have. So Cn has a name, and it's going to be cyanide. So cobalt cyanide. Now again, because we know that cobalt has multiple oxidation numbers, we have to go back and figure out what is that oxidation number going to be. So I'm going to go back to the slide that has the information. Cobalt can have either a 2+ or a 3+. Let's figure out which is the one that makes our compound equal to 0. So we have cobalt cyanide. Well, cyanide has a little negative, and that really just represents -1. And there's 3 of them. So -1, -1, -1, for a grand total of -3. And we said that cobalt could have a +2 or a +3. So because we know the rule is that they have to equal to 0, I'm going to go with the +3 because that will cancel out the -3. So because I chose +3 as my charge, Roman numeral 3 is the one that belongs in the name. So CN3, its name would be cobalt-3 cyanide. Let's look at one more example. We have 1, 2, 3. Got 3 different elements, which means that this is going to be a ternary, which means that it's going to have a polyatomic. So we have to find it on the list of the polyatomics on the left. So V stands for vanadium. And I know that vanadium is also going to have multiple oxidation numbers. So I know I'm going to need a Roman numeral at some point. And then PO4. So we're going to look on our polyatomics list. Right here towards the bottom, we see PO4. That -3 just tells me that its charge is -3, right? Now, on the formula, I am told that I have 2. Here's important. Please do not get confused. These 2 numbers tell you different things. The 4 is part of the polyatomic. That's the reason it's inside of the parentheses. the 2 on the outside tells us that there's 2 of them. So that means that there's 2 -3s for a grand total of -6, right? Now, let's look at vanadium. Vanadium is a transition metal that has multiple oxidation numbers. And the options are +2 and +3. So I'm going to go back to my formula, and I'm going to write a +2 and a +3. Now, on the formula, I am told that there are 3 of them. So I'm going to go back and I'm going to figure out, okay, well, which one is the one that if I have 3 of them, is going to add up and is going to cancel the -6 right here that we calculated earlier. So hopefully you guys can see that we're going to have to go with the +2s because they add up to +6, which cancels out the -6. The +3 adds up to +9, and that's not going to work, right? So I'm going to scratch it off. So vanadium, and since I went with the charge of +2, I'm going to write Roman numeral 2. Remember, the Roman numeral represents the charge, not how many of them there are. Okay, so don't get confused. One of the most commonly mistaken and confusing things that students tend to encounter. So we have vanadium 2, and then the name of PO4, because it's a polyatomic, we just find it on the list, and that would be phosphate. So vanadium 2 phosphate. All right, so let's take a moment and process all this information. It is a lot of information that we are slowly building onto. So let's look at some more examples, but now let's go from the name and let's write the formula, because that's the first time we're going to do that in these lessons. So I have 4 different examples. The first one here is going to be potassium chlorate. So there's a couple of steps that we have to follow. It's basically naming but backwards. We have to find the symbols first, and then we have to figure out a way that they're going to equal to 0, because that's the rule. They have to be neutral. So potassium is K, and chlorate. See how the ending ends in ATE? Well, that tells me automatically that that's a polyatomic. So it's not always the case, but it's pretty much going to be the majority of the time. If something ends in ATE or ITE, we're talking about a polyatomic. So we're going to be able to find that on the list of polyatomics. Now, if it ends in IDE, chances are it's just going to be an element on the periodic table, okay? So because this one, my first example, ends in 8, I know it's a polyatomic, so I'm going to go find it on the list of polyatomics. So if we go down the list, we find it right here, chlorate. This is its formula, so ClO3. And that little negative sign at the top tells me that its oxidation number is -1. So now let's go back to potassium. Well, potassium is in group 1 of the periodic table, and every element on group 1 is going to have a charge of +1. So if you guys notice, the charges cancel each other out, right? +1 cancels out with -1 equal to 0, right? So once you figure out that they equal to 0, then that's it. That's your formula. So just put them together, KClO3. And the name of it is potassium chlorate. Let's look at 3 more examples. Aluminum is Al. Nitride ends in IDE. So I knew that that's going to be an element. So I'm just talking about regular nitrogen. Besides, if I look for the word nitride on the polyatomics list, is nowhere to be found. There's something similar, nitrate and nitrite, but they're not the same thing. Spelling counts, right? Because these are completely different compounds and elements. So here, again, because we end in IDE, we're just talking about the regular element. So we have aluminum nitride. Now, we figured out the symbols. Now we have to figure out their oxidation numbers. Aluminum is in group number 3, and its oxidation number is +3. Nitrogen is in group 5, and its oxidation number is -3. So because these 2 oxidation numbers are going to cancel out and equal to 0, we can then assume that you just have 1 aluminum and 1 nitrogen. So its formula would be AlN. Let's look at another example. We have magnesium, Mg, and we have hydroxide. Now for hydroxide, I know it ends in IDE, but if we were to write the name of hydrogen, we wouldn't say hydroxide, we would say hydride, right? So it can't be hydrogen. That's not the way we would name it. So that means that it has to be on the polyatomics list. Again, because hydrogen, if we added the IDE, we would say hydride, not hydroxide. So we're going to have to find it on the polyatomics list. And it is right here, OH minus 1. So OH minus 1. Now, here, magnesium is going to be on group number 2 on the periodic table, so it's going to have its oxidation number as +2. And here you guys can see that the numbers don't cancel out to 0. So that means that I need another hydroxide. So what I'm going to do is I'm going to write it again, right? So -1, -1. Now that cancels out to 0. So I needed 2 hydroxides to cancel out with the 1 magnesium. So whenever you write the formula here is where you're going to use parentheses. And you only use the parentheses when we're talking about a polyatomic. So we're going to say magnesium OH, parentheses, because it's a polyatomic. And since I had to write its oxidation number twice, I will write a 2 on the outside. Okay? So that's how we are going to write the formula from the name. Let's look at this very last example. We have copper sulfate. Now for copper sulfate, I did make a mistake whenever I made the PowerPoint. So I do apologize for that, guys. I'm supposed to have right here a Roman numeral, but I think this is a really good lesson for us to learn because this is an example of why it matters in the name to have the Roman numerals. Let's just try it out and see if we can actually figure out the formula. So copper is Cu and sulfate ends in ATE. And remember, any ATE or ITE is going to be a polyatomic. So let's find it on the list. Sulfate is right here towards the bottom. SO4 -2. So SO4 -2. Now, you might be tempted to just write CuSO4. Well, let's look at copper. Copper is a transition metal that has multiple oxidation numbers. Let's look at what those are. So copper can have either a +2, oh, nope, that's cobalt. Copper can have a +1 or a +2. Now let's go back over here to the question. So it could be a +1 or a +2. And you might be tempted to just say, oh, well, it has to be the +2. But we don't know that. For all we know, it could actually be the +2. So without the Roman numeral, it's very difficult for us to figure out which of the 2 charges you're supposed to go with, because you can make either one of these to work. You could have 2 +1s, right? And your formula could be Cu2, because there's 2 of them, SO4, or it could be CuSO4, because the 2's would cancel, right? So 1 of each, or 2 coppers to cancel out the -2. So this is a clear example of why it's so important in the name to have the Roman numeral, because then you end up with a problem like this, where you technically wouldn't know which one of the 2 formulas it should be. So I do apologize for that, guys. I did mean to put a Roman numeral. However, this is a great lesson for us to learn as to why having Roman numerals is so important. So for today, we're going to do some extra practice whenever we log into our Schoology account. So make sure, you guys look at that and also compare your answers to the answer key that will also be posted. Thank you guys so much for watching.